Last time we talked about flow and we saw the Ford-Fulkerson algorithm. And we also saw that using that algorithm, we could prove a theorem. And the theorem was the mean cut max flow theorem. So the maximum flow between our source and our sink was the same as the minimum capacity among all cuts. Okay. But this is a theorem which is very similar to the theorems we've had about matchings. So for example, we had this theorem of maximum matching and minimum vertex cover. So we want to see if there is any relationship between matchings and flows, and especially in bipartite graphs. So this is the first thing I want to talk about today. Suppose that we have an algorithmic problem, and suppose the problem is this. In the input, you are given a graph G, but this graph is bipartite. So I have a bipartite graph G in my input. Okay, and I want to find a maximum matching, or maybe the size of a maximum matching. It doesn't really matter. You can find the size or you can find the matching itself. Okay. So this is the maximum matching problem in bipartite graphs. Now, we've already seen one algorithm for finding maximum matchings, and that algorithm worked in every graph, right? And the algorithm was, I'm going to start with any matching. Let's say I start with the empty matching, or I just find some maximal matching. And then I'm going to keep augmenting it. I'm going to try to find an augmenting path. And if I succeed, I can increase the size of my matching. And if I don't succeed, if there is no augmenting path, then the matching is already maximum. We've proven that. But now I want to give you a different algorithm. And now I have a bipartite graph. Okay. So let's consider this. Suppose that I have the two parts of my graph. I'm going to draw a very small graph in this case. And let's say these are the edges. Because this graph is so small, you can just take a quick look and you can say, well, maximum matching size is 2. Right? You can match everything on the right. Like you can, for example, take this edge and this edge. But here's what I'm going to do. I'm going to turn this into a directed graph. I'm going to add orientations to the edges. And I'm going to orient all of my edges from left to right. So I'm going to think that all of the edges are going like this. Right? And now I want to turn this into a network flow problem. So I'm going to assign a capacity to every edge. And I'm just going to assign a capacity of 1 to every edge. So this edge has capacity 1, this one has capacity 1, this one has capacity 1, this one has capacity. But if I want to solve a network flow problem, I should have a source and a sink. So I'm just going to add a source and a sink. So I add a source here, and I add a sink here. And I connect the source to every vertex on the left. And I connect every vertex on the right to the sink. Okay. And I'm going to give this capacity 1 as well. So this is how I'm changing my graph. I started with a graph G. First, I orient G from one part to the other part. So from left to right. And then I add 2 new vertices, a source vertex and a sink vertex. And then I add edges from the source vertex to everything on the left and from everything on the right to the sink vertex. Okay. And all of my edges have the same capacity point. I claim that if I find the maximum flow in this new graph, that's going to give me the size of the maximum matching in my origin. Okay. So can you see why that's the case? So let's call the original graph G. So I'm going to say G is my original graph. And let me call this new graph that I created here by orienting G and adding 2 vertices. Let's call that H. Okay. So this is my claim. I want to say that the maximum flow from S to T in H is equal to the size of the maximum matching G. Okay. So to prove this, I mean, you want to prove 2 numbers are equal, you just prove that each one of them is less than or equal to the other one, right? So let's say I have a matching in my original graph G. So for example, I had this matching, let's say. Okay. A matching of size 2. I can create a flow that has the same value, right? I can create a flow of 2 now, because I can just send 1 unit of flow from S to this vertex and then use the matching edge to send it to this one, and then use this edge to send it to T. And then I can do the same thing basically for every edge of my matching. I can send 1 unit of flow from S to the left side of that edge in the matching, and then to the right side, and then to T. And because this is a matching, I'm not going to use any of the edges, any of the red edges here more than once. So I'm going to get a valid flow. I'm not going to exceed the capacity of any edge. So this proves that the size of the maximum matching is less than or equal to this max flow. Because whenever I have a matching, I have a flow of the same size. So max flow has to be greater than or equal to max matching. But now let's consider the opposite case. Suppose that I have some flow from S to T. Why would that give me a matching? So I'm finding my flow using the Ford-Fulkerson algorithm, and all of my capacities here are integers. Right? So in every edge, my flow is going to decide to either send only 1 unit of flow or nothing. Right? That's how my max flow looks like. So some of these edges are going to be used in my flow. They're going to have a flow of exactly 1, and the rest are not going to have any flow at all. So I say consider the edges that have a flow of 1, and forget the red edges. Only consider the edges that have a flow of 1 here. And I claim that that gives you a matching in the original graph. Okay. So why is that the case? Well, because suppose it doesn't give you a matching. Suppose that I have 2 different edges here that have a flow of 1, but they share an endpoint. So for example, let's say I've sent a flow of 1. Let me use green for my flow. I've sent a flow of 1 through this edge, and I've also sent a flow of 1 through this edge. But where did this flow come from? It has to come from this edge, from S to this starting point. But I can send at most 1 unit of flow here, so I cannot magically suddenly have 2 units of flow going out. Okay. Now I can say the same thing for the other side. Suppose that I have 2 edges used in my matching that share the right endpoint. So I have this edge, and let's say I'm sending, in my flow, not in my matching. So let's say I'm sending a flow of 1 through this and a flow of 1 through this. Again, I have a problem with preservation of flow because 2 units of flow are coming into this vertex, but I can only send 1 unit of flow out. Okay. So my flow is definitely going to give me a matching. And it's also easy to check that the number of edges in this matching has to be exactly the amount of flow. So we proved that the maximum flow from S to T in H, I forgot to write T here, is the same as the size of the maximum matching G. Now, this is what we call a reduction. And you will see many more of these reductions in 3711 and 3721. So in algorithms and complexity theory. Basically, the idea here is that as long as you have an algorithm that solves maximum flow, you can also solve maximum matching, maximum bipartite matching, right? So it doesn't matter what algorithm I'm really using for my max flow. Maybe I'm using Ford-Fulkerson, maybe I have some other algorithm. The important point is that if I have an algorithm that solves max flow, which I do, then I can solve maximum bipartite matching. Okay. So this means that in a sense, max flow is a harder problem than maximum bipartite matching, because if I can solve max flow, I can definitely solve this one too. So that's why we call this a reduction. We're reducing maximum matching to maximum flow. Okay. Or another way of looking at it is that if only I could solve max flow, I could also solve max matching, bipartite matching. We're going to see just one more topic about matching, and this is the stable matching theorem. So here's the problem. Our problem is actually a dating problem. So suppose that we have n men and n women. And they're dating, and we want them to get married. So we want to create a perfect matching. We want to match every man to exactly one woman and every woman to exactly one man. Okay. Now, the issue is that each of the men and each of the women have preferences about who they want to pair with. So let's say I have n men. Let's give them some name. So let's call them M1, M2 to Mn. And I have n women. Let's call them W1, W2 to Wn. So every woman, Wi, has a ranked list. So she has some preferences about the men, and that preference is basically a ranked list of all the men. Okay, so has a preference. Or another way of looking at this is that the preference is basically a permutation of the men. Okay, so this is like Mi1 is preferred to Mi2, who's preferred to Mi3, so on to Min. But this is the preference of woman I. Okay. And the same thing for all the men. So every man also has a preference, which is a permutation of the women. And we assume that everyone is willing to marry everyone else. So imagine that we have a complete graph, so a complete bipartite graph, and we want to match every man to every woman, and we can make any kind of matching that we like. Okay, but there is a problem of lack of stability. So here's what we say. Suppose M is a matching, and let's say it's a perfect matching. And by perfect, I mean that every man is matched and every woman is also matched. And let's say that this one has matched all the people. And suppose that I have a man Mi and a woman Wj that are not matched to each other. So Mi is going to be matched to another woman, and Wj is also going to be matched to another man. So we say this matching is unstable if Mi prefers Wj to his wife and Wj prefers Mi to her husband. Okay, So if this pair prefer each other to whoever they're matched to, that's called an unstable marriage. And basically what happens is they get divorced and they marry each other, right? So this is, we say the pair MIWJ is unstable if MI prefers WJ to his match, and also WJ prefers MI to her match. As you can imagine, we say that a matching is stable if every pair is stable, if we don't have any unstable pairs. Okay, so a matching M is stable if there are no unstable pairs. So here's the theorem that I want you to prove. I want you to prove that a stable matching always exists. So there is always a stable perfect matching. They always, I mean, no matter what the preferences are. So with any combination of preferences, there is always at least one matching M, which is perfect, meaning that it matches everyone, and it's stable, which means that it doesn't have any unstable pairs. Now, one way of proving theorems in general, which is also very good, especially for theorems in graph theory, is that whenever you want to prove something exists, you just construct that thing. You give an algorithm that creates what you want to prove should exist. And then you say, because this algorithm succeeds, then this should exist. So in other words, if I can give you an algorithm that always produces a stable matching, then that means that a stable matching always exists, right? Because there is an algorithm, so the algorithm always works. Okay. Now, this algorithm is probably the funniest algorithm in all of graph theory. This is how this works. We say that our algorithm consists of several iterations. So think of every iteration as one day, okay? So we have several iterations. And here's what happens. In every iteration, we do these things. So the first thing we do is that every man looks at the top of his list, finds the woman that he prefers the most, and proposes to her. Okay. But if this same woman has rejected this man before, she's removed from the list. So at the beginning of every day, every man just goes and proposes to the most preferred woman who has not rejected him so far. Okay. So every man proposes to his most preferred woman who has not rejected him yet. And of course, this is based on the preference of this particular man. Okay. So now the women get a bunch of proposals. We consider two cases. The first case is that every woman has received exactly one proposal. So we say if every woman has exactly one proposal, they all accept. Now, we are assuming here that the women are actually collaborating with each other. So this is a global check. We are checking if all the women have each exactly one proposal, then they all accept. Okay. Now, otherwise, if this is not the case, then some women will have 0 proposals and some women will have more than one proposal. So this is the next thing that we do. Say otherwise, every woman who has more than one proposal what should she do? Yes, rejects all of the proposals except the most preferred one. Okay. Rejects all but the most preferred. And again, this is by preference of this particular woman. Now, importantly, she doesn't accept the most preferred proposal. Okay. She just says maybe and waits for future times. And let's say says maybe to the top proposal. Okay. Now, why is this the case? Intuitively, the idea is that, well, I have a bunch of proposals today. I look at the top proposal. I know that I have to reject everyone else. But maybe tomorrow I'm going to get an even better proposal. So I shouldn't say yes to the top proposal. Okay. So she just says maybe to the top proposal. But importantly, maybe is not no. Maybe is not a rejection. So basically what happens is that in the next day, in the next iteration, the same man will again propose because he's not rejected. Okay. So the idea here is that if you look at it from the point of view of this woman who has more than one proposal, it's safe to reject the non-optimal proposals. And it's also safe to say maybe to the top one because he's going to propose tomorrow anyway. Right? Okay. This is the algorithm. This is the whole algorithm. Okay. And we claim that this algorithm produces a stable, perfect match. Okay. Why? So whenever we say that we have an algorithm to prove the existence of something, the first thing we have to prove is that our algorithm terminates. Our algorithm should not run forever. So why does this algorithm finish? So you have to give me a proof that this algorithm cannot run forever. Yeah, so one way we can prove that the algorithm finishes is if we find some value that is decreasing and we say that this value cannot decrease forever. Okay, so kind of like an infinite descent kind of. So what I want to do here is I want to say there is something that is decreasing. And what decreases here is basically the list of women that each man is willing to propose to. Right? So whenever, so suppose at the very beginning, every man has a list of n women, but if he gets rejected by the first woman, now he has a list of n minus 1 women. If he gets rejected by the second woman, he has a list of n minus 2 women, and so on. Okay? So if I look at the sum of the sizes of the lists of all the men, That's what's decreasing here. So at every iteration, either I get to this point, in which case the algorithm terminates, they all accept, and I found the perfect matching. Or if I'm here, it means that at least one woman is rejecting one man, right? Which means that the total size of the lists of the men is decreasing. And this total size cannot be less than 0. So this algorithm terminates. Okay. So far, all we know is that this algorithm terminates, and we know that it can only terminate with this red line here. So when it terminates, it's going to give us a perfect matching. It's going to give us a matching where every woman has exactly one proposal and they're accepting. But why is this a stable matching? So you have to again look at this algorithm from the point of view of men and the point of view of the women. So from the men's point of view, they're starting with the most preferred woman and they're going down. So for every man, the preference is going down. But if you look at it from the point of view of the women, so suppose that a woman has said maybe to one man today. If she says maybe to another man tomorrow, that means that the second man was more preferred, right? So the list of men who are getting the maybe answer is actually an increasing list. It's getting better and better for women, right? So these are the two properties that we have. For every man, the women that he's proposing to are getting worse and worse. For every woman, the men that she's saying maybe to are getting better and better. Okay? So now suppose, to get a contradiction, suppose that we actually have an unstable pair. So this is proof by contradiction. So I say, suppose MI WJ is an unstable pair. Okay. So this means that our algorithm ended here and WJ accepted the proposal of MI, but somehow it's unstable. Sorry, no, something, I completely made that. Yeah, I was wrong there. If MI and WJ are an unstable pair, it means that they are not matched to each other, right? So the unstable part is that, let's say MI is matched to WI and WJ is matched to MJ, but MI-WJ is an unstable pair, which means that MI prefers WJ to WI and WJ prefers MI to MJ. Okay. I want to say that this is impossible. Okay. So here, MI is matched to WI. But remember the algorithm from the point of view of MI. MI was proposing to the most preferred woman and then just going down the list. So if MI is matched to WI, it of course means that at some point MI proposed to WI, but MI prefers WJ. So it means that before proposing to WI, MI proposed to WJ, right? Okay. But here's the thing. So when MI proposed to WJ, now let's look at it from the point of view of WJ. WJ has rejected MI, right? Because otherwise, MI would be matched to WJ in the end, right? MI has gone down his list, so that means WJ rejected MI. But if WJ rejects MI, it means that it was in this case. It means that WJ had a proposal better than MI, right? And we also said that the list of proposals to which WJ says maybe is increasing in quality from WJ's point of view, right? So it's impossible that WJ rejects the proposal of MI, but then later accepts a worse proposal. So that's not going to happen. So we don't have an unstable pair. This algorithm always produces a stable perfect match. Okay. Now we're going to completely leave the world of matchings and we're going to go to a different world. We're going to talk about coloring of graphs. So we've seen a little bit about graph coloring in this course before, but we're going to see more. So graph coloring. So you've already seen in the homeworks and problem sets that I talked about bipartite graphs being the same as two colorable graphs and like tripartite graphs being the same as three colorable graphs and so on. We're going to define this officially and formally. So we say that given a graph G, and this graph can be directed or undirected, you'll see that it doesn't really matter for our definition. Given a graph G, a proper coloring with K colors is just a map or a function. Let's call it C, that maps every vertex of my graph to a color. And this color is going to be one of the numbers from 1 to K. Okay, so I have a graph. I'm assigning a label to every vertex, but I'm thinking of that label as a color. And I have K possible colors. Okay, so we say this is a proper coloring if for every edge, E, the two endpoints of E get different colors. Okay. Now, yeah, my graph was with vertex set V and edge set E. Now, as you see in this definition, it doesn't really matter if I have a directed graph or undirected graph, because at the end of the day, I'm saying the two endpoints of every edge should have different colors. So it doesn't matter if the edge is going in this direction or that direction. Okay. Now, in this course, I often just say coloring, and what I mean is proper coloring. I don't want to just repeat the word proper. So whenever I say I have, for example, a 5 coloring, I mean I have a proper coloring with 5 colors. Okay. Great. Now, we can also define something called the chromatic number. The chromatic number of a graph is the minimum number of colors that we need in order to find a proper coloring. Okay. So the chromatic number, and it's written like this. This is a Greek letter that I cannot pronounce. So the closest thing I can pronounce to this is chi, but it's not. You can give it to Google Translate, it will pronounce it for you. So the chromatic number chi of G is the least number of colors needed for a proper coloring of G. So for example, if a graph is two colorable, that's the same as saying that my graph is bipartite, right? Because if I have two colors, if I have some red vertices, let's say, and some blue vertices, if this is a proper coloring, no edge will have the same color on both sides, right? So that means that all of my edges are going from red to blue. So I can think of the red vertices as one part, and I can think of the blue vertices as the other part. And this is a bipartite graph. So bipartite and two colorable are basically the same. Great. Now we want to prove something, some bounds on how many colors we will need to color a graph. So first of all, I'm going to remind you of two definitions. So first of all, an independent set is a set of vertices that have no edges between them, right? So independent set is that I subset of V is an independent set if there is no edge with both endpoints in I. So basically the idea is that if I only keep the vertices in I, and if I remove all the other vertices, there would be no remaining edges. And then kind of the opposite of independent set is a clique. If I have a set C, subset of vertices, this is a clique if every two of the vertices are connected to each other, every two are neighbors. If for every two vertices U, V in V, there is an edge from U to V. Sorry, not in V, in C. There is an edge from U to V. Okay. So an independent set is a bunch of vertices such that there is no edge between them. A clique is a bunch of vertices such that all the possible edges between them are already there. Every pair of them are connected to each other by an edge. Okay. And as we've seen before, whenever we define things like this, we want to ask, what is the biggest one? What is the smallest one? It's kind of trivial to find the smallest independent set. You can take the empty set, or you can take just one vertex if you don't want the empty set. And the same for clique. So what's interesting for us is what's the size of the largest independent set in a graph? Or what's the size of the largest clique in a graph? And what's even more interesting is to somehow connect that to the chromatic number. To say, how many colors do I need to color my graph based on the sizes of my independent sets and cliques? But before that, I just remembered one more point. Is this chromatic number even well defined? So I'm saying chromatic number is the least number of colors that I need to color the graph G. Can I color any graph? So if I have a simple graph, yes. But what happens if I have a loop? So if I have a vertex U and then I have an edge from U to U, then I cannot assign any color to U because the two endpoints of this edge are going to have the same color anyway. Okay, so this is why we talk of simple graphs in this course, because loops are terrible. Loops always create problems for us. Oh, and by the way, if you go back to the algorithm that I gave you in the last session for finding maximum flow, that algorithm also breaks down if you have a loop. So make sure you don't have loops there. Okay, coming back here, imagine in this session that none of my graphs have loops, but can I have like multiple edges? So suppose that I have two vertices U and V, and instead of just having one edge between them, I have several edges. This doesn't matter, right? Because as long as I have one edge between U and V, I have to assign different colors to U and V. Now, if I have three edges, it's the same constraint. So if I have several edges, it's the same as having just one edge. Okay. So because of this, we don't allow loops and we don't consider repeated edges. So we're just assuming that all of our graphs are simple. Okay. So let's prove some theorems. This is my first theorem. I want to say that in every graph G, the chromatic number of G is greater than or equal to the size of the largest clique. Okay, actually, you know what? Let's give it a name. So let's say that I show the size of the largest clique of G with omega of G. This is not W, this is omega. So this is size of a largest clique. And let me do the same thing for independent sets. So I use alpha here. This is the size of a largest independent set. Okay. So I want to prove that the chromatic number is greater than or equal to omega of G. This is kind of obvious, right? So let's say I have, for example, a clique of size 4. So that means that I have 4 vertices, and every 2 of them are connected to each other. Okay. And I want to color this graph, let's say. Now, if I assign some color here, I cannot assign it to any of the other vertices because all of them are connected to this vertex. So I have to assign a different color here. And then I have to assign a third color to this vertex. And I will have to assign a fourth color to this one, right? So basically the idea is that whenever I have a clique, all of the vertices in this clique are connected to each other. So all the vertices in this clique should get different colors. And it doesn't matter if this clique is not my entire graph. So maybe my graph had some other things going on. I don't know, right? At the end of the day, every vertex here is connected to every other vertex here. So no matter how I color my entire graph, I have to give different colors to the vertices of my clique. So if this is the size of the largest clique, I just look at the largest clique and I say I need at least these many colors. Okay, great. Now let's do the second theorem. So this gave me an kind of a lower bound, right? So it's saying that I need at least these many, but can I get an upper bound? So let's consider this. I want to say that the number of colors I need is less than or equal to the number of vertices divided by the size of the largest independent sets. Less than equal or greater than equal? I'll figure that out. Greater than equal, I think. Okay. Now, why is this one the case? Why do I need at least these many colors? So suppose that I have a graph and suppose that I have colored it with K colors. Okay. And then I look at all the vertices of color 1. All vertices of color 1 are going to be an independent set. Because by definition, if it's a proper coloring, it's not going to assign color 1 to 2 endpoints of the same edge. So if I consider all the vertices that have color 1, there is no edge between them. They're an independent. If I consider all vertices of color 2, they're also an independent set. So if I have a proper K coloring, what's going to happen is that I'm going to have a bunch of independent sets. These are all the vertices with color 1. These are all the vertices with color 2, so on, and vertices with color K. Right. And I know that any edge goes from one color to another color. but I cannot have an edge like this that is entirely in the same color. That's not possible. Okay. So how big is each of my independent sets? Well, alpha was supposed to be the size of the largest independent set, right? So every independent set has size alpha or less. Okay, so all of them together are going to have a size of at most k times alpha, right? But all of these independent sets together are covering all of my vertices. So k times alpha is greater than or equal to n. Or less than equal or greater than equal. I'm really sleepy today again. Yeah, no, it's greater than or equal to n. Because each of these is at most alpha, and then I have k times alpha. So k times alpha is greater than or equal to n, which means that k is greater than or equal to n over alpha. Okay. And now to go from k to the chromatic number of G, just pick k to be the smallest possible k where you can have a k coloring. And that's like the chromatic number of G. And this theorem holds for any k where you can have a k coloring. So we prove this, that the chromatic number is greater than or equal to n over alpha. Okay. Yeah, but I'm not very happy with these theorems because they're telling me that I need more than some number of colors. I want to see the other side. I want to see theorems that tell me if you have this many colors, it's enough. You can color your graph. Well, a very trivial theorem would be that if I have n colors, that's definitely going to be enough. I don't have self loops. I just color every vertex differently. And then I colored my whole graph with n colors. So n colors is enough. But is there a graph that needs all the n colors? Yes, the complete graph needs n colors. Because again, the complete graph, so basically, if you think about it, a clique is just a complete graph, and an independent set is just an empty graph. So we've already seen that a clique of size k needs k colors. So a clique of size n, which would be the complete graph, needs n colors. Okay, but can I do better than this? So here's another theorem. I say, suppose G be a graph. So let G be a graph with maximum degree delta. So I'm looking at all the vertices. I'm asking, what is the maximum degree among all of them? And it's delta. Okay. I claim that the chromatic number of G, by the way, I forgot if this was supposed to be written like this or like this. I don't know. I don't know Greek. The chromatic number of G is going to be less than or equal to 1 plus delta. So if my vertices have different degrees and the largest degree among my vertices is delta, then I need at most delta plus 1 colors to color all of my graph. Now, again, this is one of those theorems where we give an algorithmic proof. So to show that this actually works, I'm going to give you an algorithm that colors the graph with at most delta plus 1 colors. Okay. And this is going to be the stupidest algorithm, again, that you've ever seen. Because this is called greedy coloring. It's literally what kindergarten students do when you give them a graph to color. So you just pick a vertex and color it with the smallest color that you can. So you pick a vertex, you say, can I color it with color 1? Well, for the first vertex, you can. And you keep doing this. Whenever you pick a vertex, you look at all the colors that are used in its neighbors before. and then you just assign the smallest color that was not used in any of the neighbors. Okay, so pick any vertex, or pick any order for coloring. So just take any permutation of the vertices. When coloring vertex I, assign the smallest color J not used in neighbors of I. Okay. That's it, that's the algorithm. Now, why does this work? So what is the largest color number that you might have to assign? So let's just do this. Let's say I have this graph. I just start coloring. Let's say I start here. I assign color 1. This one already has 1 in one of its neighbors, so I assign color 2. I want to assign a color to this one. I see that I can assign 1 because 1 is not used in any of the neighbors, so I just assign 1. Now I want to color this one. I see that 1 is used in the neighbors, so I assign color 2. Now I want to color this one. I see that 1 and 2 are already used in its neighbors, so I assign color 3. And then when I get to this one, I see that 1 is used in the neighbors, but 2 is not, so I assign 2. Okay. Now, very importantly, this algorithm doesn't give you an optimal coloring. You can easily color this graph with 2 colors, right? Just assign color 1 here, 2 here, and 1 here. Every column gets a different color. But this algorithm gives you a coloring with 3 colors in this case. And what we're claiming in general is that if the maximum degree is delta, I'm going to use at most delta plus 1 colors. Okay. So just look at every vertex when it's being colored, and let's see what is the color that we're assigning to it. So when I'm coloring vertex I, I'm assigning the smallest color that was not used in the neighbors of I. But how many neighbors can I have? I can have at most delta neighbors because that's the maximum degree. So at most delta colors are used in the neighbors of I. So the color that I'm going to assign to I is not going to be larger than delta plus 1. So, and of course, you can easily check that this is going to give you a proper color. You will never have an edge that has the same color on both sides. So this simple algorithm colors the graph with delta plus 1 colors. So the chromatic number of G is at most 1 plus that. Okay, but can I do better than this? Well, in general, kind of no, because you can find examples where you need delta plus 1 colors. So one example of that would be a triangle. Right? If I have a triangle, here delta is 2, and I need 3 colors. Or generally, if I look at any odd cycle, I have this property. So in any cycle, the degree of every vertex is 2. So if I have an odd cycle, I need at least 3 colors. I cannot color an odd cycle with 2 colors because that was literally the most basic theorem we had, that a graph is bipartite if and only if it doesn't have an odd cycle, right? So I need at least 3 colors to color an odd cycle. So for odd cycles, I cannot do better than delta plus 1. Can you think of any other family of graphs for which I cannot do better than delta plus 1? Stars? No. For a star, I only need 2 colors, right? We have complete graphs as well, right? So if I have a complete graph on n vertices, the largest degree is n minus 1, but we've already seen that we need n colors. Now, there is a very interesting theorem of Brooks, which we're not going to cover in this course, which says that these are the only graphs where you need delta plus 1 colors. So in any other graph, delta colors are enough. Okay. So the only graphs that actually need delta plus 1 colors are the odd cycles and the complete graphs. But anyway, let's try to do something else. So I cannot find an algorithm that gives me a result better than delta plus 1 because I know graphs where I cannot do better than delta plus 1. But maybe I can have a more complicated formula, like why should this only depend on delta? I've already seen here that it can depend on alpha or omega or so on. So let's just look at more parameters. And the first idea that comes to mind here is to say, okay, instead of looking at all of my, instead of looking at the maximum degree, let's look at all of the degrees, right? And instead of just saying, I want to pick any order for coloring, let's maybe find a better order for coloring my vertices. Okay. So consider this graph here. We colored it with 3 colors. Let's say we're not very happy with that. Let's see if we can do better. First of all, I'm going to look at the degrees of the vertices. So this one has degree 3, this one has degree 2, this one has degree, I can't count, 4. This one has degree 3, 2, and 2. Okay. So in the greedy coloring, we said that we just pick any ordering of vertices. But I can sort my vertices by degree. Now, which one do you think would give us a better result? If I sort them in increasing order of degree or in decreasing order of degree? So do you prefer to start with vertices of small degree and color them? Or do you prefer to start with vertices of large degree? Large, yes. Because like intuitively, the idea is that when I do some coloring, when I've already colored part of my graph, now I have some restrictions on what colors I can assign to the rest of my graph. So I prefer the remaining vertices to have small degrees so that I have less restriction. Okay, this is very hand-wavy. This is not a real mathematical argument, but let's just see what this idea gives us. So I'm going to say, I want to color my vertices starting from the vertex with maximum degree. So I assign color 1 here. And then let's say I want to assign a color here. I know that I cannot assign 1. So I assign 2 here. And I want to assign a color here. And I've already used 1 and 2, so I'm assigning 3. Okay. So I'm going to stop it here. Of course, we can continue coloring this graph, but as you see already, in this case, it's not going to give us a better color. Even though I know that the optimal coloring has only 2 colors, in this case, I'm already getting, no, actually the optimal coloring has 3 colors, right? I have a triangle here. Yeah, I forgot that I had this edge. Yeah, this is the optimal coloring, okay. Yeah, 9 a.m. classes are not really great for me. So I cannot count, I cannot see the edges that I'm drawing. Anyway, so I start with the largest degree and I color like that. So, and then I have to assign a color here. I can assign 2. I have to assign a color here. I can assign 2, and here I can assign 3. Okay. So on this example, it seems like changing the order didn't help us. But would it give us a different bound in general? And the answer is yes. And would it help in general? Well, it really depends on the graph that you have. So this is the next theorem that I want to prove. I want to say, suppose G is a graph. And let's say that I know the degree sequence of G. So I know the degrees of all the vertices. And let's say that the degrees are D1, D2 to Dn. And D1 is the largest degree. Okay. So let's say that I apply the greedy algorithm, but I start with the vertex that has the highest degree, and basically I go D1, D2 to Dn. I color greedily in that order. What kind of bound would that give us? So this is the bound that I'm going to claim here. I'm going to say that the chromatic number of G is at most this thing. The maximum, okay, 1 was the maximum over every I of the minimum of di and I minus 1. So what I'm saying here is go over this sequence, and at every point in the sequence, compute the minimum of di and I minus 1, and then take the maximum of that over every index I. And I'm saying that's the number of colors that you will need at most. Okay. Now, this might look weird, but this is just coming out of the analysis of this algorithm, and we're going to do it, and you're going to see where this came from. So a lot of theorems in math, and especially in discrete math and parts of math that are used in computer science, are kind of weird in the sense that if you see the theorem, you might not know how to prove it, but there is a very natural explanation for where this theorem came from. And the natural explanation is that people knew this algorithm, the greedy coloring, and then they were thinking, okay, suppose that I just, instead of picking any order, I pick the order of decreasing degrees. So I start with the highest degree and I start coloring like that. And then they were thinking, okay, let's analyze this algorithm and see what kind of bound it gives us. And this is the bound that it naturally gives, and we're going to see that. Okay, so let's look at this. Let's say I have my degrees, D1, D2, so on. At some point I have, let's say, DI, and then I have DN. And of course, these are degrees of vertices, so I have one vertex corresponding to each of these. Okay. And now I'm saying this is my coloring order, so I'm going to start coloring from left to right. This is my coloring direction. Okay. So when I'm coloring D1, what is the color that I'm going to assign to it? I'm definitely going to assign color 1. Right. When I'm coloring D2, what is the color that I'm going to assign there? Well, if D2 is not a neighbor of D1, then it also gets color 1. If D2 is a neighbor of D1, then it gets color 2. Right? So this is going to get color 1 or 2. But what I want to analyze is the general case. Suppose that I have already colored the first I minus 1 vertices, and I've got to the vertex that has degree di. I want to see what is the color that I'm going to assign to di. Okay, so I have to see how many colors were used in the neighbors of di. In the neighbors of this vertex with degree di. Di is the degree, not the vertex itself, but whatever. So I want to see when I get to this vertex and I want to color it, how many of its neighbors have already been colored, right? So it has at most di neighbors. So at most di of its neighbors are colored. Okay, so if I look at number of colored neighbors, this number is definitely less than or equal to di. But what else do I know? I know that this is the ith vertex that I'm coloring. So before getting here, I've colored at most I minus 1 vertices. Okay, so the number of colored neighbors is also less than or equal to I minus 1. So when I get to vertex I, the number of colored neighbors is less than or equal to the minimum of di and I minus 1. Right? I cannot have more than di neighbors at all, so I cannot have more than di colored neighbors. And I've only colored I minus 1 vertices before this vertex, so I cannot have colored more than I minus 1 neighbors. Okay, so the color that I'm going to assign to this vertex is going to be this number plus 1 or something smaller, right? So the color assigned to di, the color of the vertex, I don't know what to call it. Let's give this vertices some name. So let's say this is vertex V1, this is vertex V2, this is vertex Vi. So the color assigned to Vi is going to be less than or equal to this number, minimum of di and I minus 1 plus 1, right? Because this is the number of colors that could have possibly been used in the neighbors of this vertex Vi. And now I have to assign a color to Vi. I might be able to assign a smaller color to Vi, but whatever color I assign, it's going to be less than or equal to this bound. Okay. Now, what did I want to prove? I wanted to prove that my chromatic number is at most this. Now, I have a way of coloring my graph. I can just color my graph and I can ask what is the largest color that I have used, right? And that largest color, I don't know if this coloring is optimal or not, but that largest color is going to be greater than or equal to the chromatic number. Because maybe my coloring is optimal, maybe it's not, right? So what is the largest color here? So I know that my chromatic number is less than or equal to the largest used color. But this is just the maximum over every I of this value, right? Because for every vertex I said that this is the color that I'm assigning at most. So if I just take the maximum over every I, that's the maximum color that I'm assigning overall. So that's where this comes from. We're going to see another coloring theorem. So let's say that I have two graphs. I want to define what we call the Cartesian product of two graphs. So let's G and H be graphs. I define the Cartesian product of G and H, and I write it like this, or sometimes we just call it the box product. So G box H. It's a new graph. And the way it works is like this. The set of vertices is going to be pairs. So I'm going to have a vertex for every pair of vertices in G and H. Okay. And then I'm going to have a set of edges. And the rule is this. I say that I have an edge from UV to U prime V prime. By the way, I can do this for directed edges or undirected edges. Again, it doesn't really matter. You can use the same definition. So I have an edge from UV to U prime V prime in the Cartesian product if one of these two cases happens. The first case is that U is equal to U prime, and there is an edge from V to V prime in H. And the second case is that V is equal to V prime, and there is an edge from U to U prime in G. Okay. So kind of imagine it like this. I have two different graphs, G and H, and when I'm taking the product graph, I'm creating a grid where I have one vertex for every combination of vertices in G and H. And then the way I can move in this grid is that I can either take a move in H or a move in G. Okay. So the simplest example is actually a grid. So suppose that G is this. G is just 3 vertices, 1, 2, 3. And H is, let's say, this graph with 4 vertices. A, B, well, too many. Let's just do 2. This graph with just A and B. Okay. If I look at G box H, it's going to have a vertex for every pair of vertices from G and H. So it's going to have a vertex 1A, vertex 1B, 2A, 3A, 2B, 3B. Okay. And now the rule is that, for example, if I'm at 1A, I can keep 1 the same, and I can take an edge that starts at A and goes somewhere else. So from A, I can only go to B, so I can go like this. Or I can keep A the same, and I can take an edge that went out of 1. So from 1, I could go to 2, so I have this edge. Okay. And if I complete it, you see that it's basically just a grid. Okay. So this is the product of those two graphs. Now, in general, I can have any graphs here. As long as I follow these rules, I can define their box products. Okay. Here's what I want to prove. I want to say that the chromatic number of G box H is the maximum of the chromatic number of G and the chromatic number of H. Why is this the case? Oh, I'm assuming that G and H are not empty graphs. Like, and they have at least one vertex. So first of all, do you agree that when I take the product of two graphs, and again, none of the graphs are empty, I'm going to need more colors, or at least as many colors in the product as I need in G? Because the product already includes at least one copy of G, right? So look at this. I had this graph G here, and how did I create the product? I basically created a copy of G for every vertex of H. I have a copy of G here. I have another copy of G here, right? So since I definitely have a copy of G in this product G box H, the number of colors needed to color G box H cannot be less than the number of colors needed to color G. And the same thing for H. So this proves that the number of colors I need to color G box H is greater than or equal to the maximum of the chromatic numbers of G and H. But it only shows that it's greater than or equal. It doesn't show that it's equal. I want to show that it's exactly equal. So I have to find a way to color this graph with exactly this many colors. Okay. Here's what I'm going to do. Suppose that I color G with, I don't know, K colors, and I color H with T colors. Okay. And let's suppose that K is greater than or equal to T. So suppose that G needed more colors than H. It doesn't really matter because this is symmetric. So the case where H needs more colors is going to be exactly the same. So I'm just going to prove this case. Okay. So what does this mean? This means that I had a coloring in G that basically mapped vertices of G to numbers between 1 to K. And I also had a coloring in H that mapped the vertices of H to numbers between 1 to T. Okay. So first of all, I kind of don't like to use numbers starting from 1 because I'm a computer scientist. I want to start my numbers from 0. Okay. So let's say that my coloring in G is mapping every vertex to colors between 0 to K minus 1. Right? It's just easier for me this way. And here, I also say that it's mapping to colors between 0 to T minus 1. Just subtract 1 from every color. But here's the thing. I can define a coloring now that maps vertices of G times H. So vertices of G times vertices of H also to colors between 0 to k minus 1. But how should I do this? So let's say I have a vertex UV. What color should I assign to UV? Well, I can just take the color of U in G, and I can take the color of V in H and just add them together, right? But my problem is that I wanted my numbers to be between 0 to k minus 1. So I do all of these things and I take this modulo k. So I take the remainder when divided by k. Now I have a way of assigning colors, that is assigning colors between 0 to k minus 1 to every vertex of my product graph. Okay, but is this a proper coloring? If I have an edge, will the two endpoints of the edge get different colors? Let's look at it here. So let's say that I've already colored G. So let's say I write my colors in this color. So let's say I use colors 0, 1, and 2. And here I use colors 0 and 1 for H. Okay. So what color am I going to assign to 1A? Sorry, actually, why did I use 2 there? I can use 0. Right. Okay, so I'm using 2 colors for each of my graphs. So my K here is 2. So what color am I going to assign to 1A? So it's 0 plus 0, which is 0. Okay, what about 1B? It's 0 plus 1, which is 1. What is the color that I'm going to assign to 2A? 1 plus 0, 1. 2B is going to get 1 plus 1, but we're doing calculations modulo 2, so it's 0, because I'm taking the remainder when divided by 2. So 2 is the same as 0. And here I'm going to have 0, here I'm going to have 1. Okay. So at least on this simple example, it seems to work. It seems that every 2 neighboring nodes, every 2 neighboring vertices are getting different colors. But why does this hold in general? Because we can go back to our definition. We said this, we said that there is an edge from UV to U prime V prime if one of these 2 cases happen. Right. So all I have to do is that I can follow this definition and I can say, well, let's show that these 2 vertices get different colors in this case, and they also get different colors in this case. That would prove that for every edge of my product graph, the 2 endpoints have different colors. Okay, so let's do this. So let's first do case 1. What's happening in case 1? In case 1, U is equal to U prime, right? So basically my edge is something like this. It's UV going to UV prime. Okay. Now, what is the color of UV? The color that I'm assigning to the vertex UV. It was supposed to be the color of U. I'm not going to write these subscripts anymore. You know what I mean. Plus the color of V, all of it modulo K. Right. What is the color of UV prime? It's color of U plus color of V prime modulo K. But what do I know about V and V prime? I know that there was an edge in H from V to V prime. So the color of V was not the same as the color of V prime. Okay, color of V is not the same as the color of V prime. Okay, and by the way, here when I'm looking at the colorings, I said that K is bigger than T. So I can imagine that this one is also mapping to all the colors up to K minus 1. Right? I'm just extending the codomain here so it works. Anyway, I want to show that this one, color of UV, is not the same as this one. But this first part is the same and the second part is different. So the sums have to be different. So these 2 don't have the same color. Okay. Case 2 is exactly the same. I'm too lazy to do that. It's basically the same thing, but in the other direction. So the second component is the same, the first component is changing. So the sum has to change. So this is a valid coloring, which shows that I could color this graph, the product graph, with exactly this many colors. And I also proved that you need at least this many colors because the product graph contains at least one copy of each of the two graphs. So the theorem is proved.